Hi, AP Chem. Welcome to our next application of acids and bases. So, one of the biggest lab techniques when you're talking about acids and bases is going to be titration. So we talked about titration in the beginning of the year, but let's just recap what titration is. So when you titrate a solution, basically, what you're doing is you have a solution that's unknown, and you're going to add something into your solution in order to make a reaction happen. And the reaction that you make happen is going to help you investigate what's actually in that unknown solution. When we're talking about titrating acids and bases, usually the question is, what's the concentration of acid in a solution? Or what's the concentration of base in a solution? So for example, let's say you have a situation where acid is leaking into a local creek, or acid is building up for some reason in a local creek, and you want to know, well, what is the concentration of the acid currently in the creek water? So you would get a solution, you would get a sample from your creek. You know it's acidic, and so you're going to add a base as your titrant. So your titrant is going to have known concentration. It's the thing you're adding. So probably you have made this base. You control everything about this base. You control its concentration. You put it in the burette. You're going to control the volume going down, and you add base into this solution in order for a neutralization reaction to occur. And so as this neutralization reaction occurs, your solution starts out very acidic. If we have a pH, a graph of pH, your solution is going to start out very acidic when it's all by itself. When you add the base, some of the base and acid react together. A little bit of the acid is going to neutralize, and you're going to have less acid. And as you add small amounts of base and neutralize the acid in the solution, you're going to have less acid, less acid, less acid. Because remember, acids and bases are going to react to form water plus your salt, right? So as you react this acid, as you add base, the base gets used up completely, reacts some of the acid, and you form water and salt, water and salt, water and salt. You're going to have less and less and less acid in your solution. Well, pretty much you're going to have no acid in your solution. You'll have all water and salt. And then when you add a little bit more base, you're going to have a basic solution, a basic solution, a basic solution. And so you get a curve on this. I didn't draw that curve very well, but you get the idea. We get a curve on here that shows the pH change in our solution. It kind of looks like a flattened S or a stretched out S. And this is kind of like the general trend of our solution. By the end, so when you have added enough base to neutralize all of the acid, the only thing you're going to have left in the solution is water and salt. The pH will depend completely on the water that's present and the salt that is present as well. At this point, usually we have added a couple things into our unknown solution, right? We have our river water containing our unknown quantity of acid. And then into here also we add what's known as an indicator. And so you may remember this from the beginning of the year. An indicator is a is a molecule that has, usually it's a weak acid. It has a weak acid format. That's one color. And when that hydrogen is removed from it and it's just the anion that's left, it's a different color. So let's say the weak acid color is blue and the ion form when it's deprotonated is yellow. So we're going to add this indicator in here as well so that when we have acid that's present, our solution is blue. As soon as we have neutralized all the acid and this base gets added, it neutralizes the indicator as well. And the salt of the indicator is left. Well, all of a sudden our solution changes to a different color. So that color change indicates to us when we run out of our weak acid that was originally in our solution. And there's no more weak acid left. The base then neutralizes our indicator. Our indicator is now in a different form and a different color, and a color change happens. That color change indicates to us where we have neutralized all the acid. Well, if we know this volume of base at this point, and we should know that volume of base because we're adding the base, right? If we know the volume of the base that we have added, we can take the volume of base and calculate using dimensional analysis to the volume of our acid. And then we figure out what the concentration of that acid is in our river, right? That is titration. And so we're going to talk through this concept of titration. We're going to talk through the math behind titration. And we're going to look at what is happening at these different points. What happens when there's only acid present? What happens when a little bit of base gets added and then consumed? What does it look like when we add enough base so that it completely uses up all of our acid? What does it look like when we add enough base to completely use up all our acid and have base left over? There are some big points in our titration that we want to be able to deal with mathematically, and we want to understand conceptually. So that's where we're going. Before we get into all of that, let's just take a look at some vocab terms. You want to be able to tell me what the titrant is. The titrant is the thing that you are fully in control of and you're adding. So that in the example I just gave you, that would be the base, right? So we choose the base we're going to use. Let's see, for river water, I'm going to use sodium hydroxide, right? We're going to choose the base that we're going to add. We're going to choose the concentration of base that we add. Would it be appropriate to use 6 molar sodium hydroxide with river water? Probably not. That's super concentrated base. We're probably not going to find super concentrated acid in river water. Hopefully we won't, otherwise everything's going to be dead in our river, right? So maybe I would choose something with a little bit lower concentration, like 1 molar sodium hydroxide or 0.1 molar sodium hydroxide, right? So I choose the concentration of my titrant. By the end, I'm also going to track the volume. I start with a specific volume, I write that down, I track the volume all the way down. When I end and I've hit that point where the color change occurs, I'm going to record that volume of base so I know exactly how much base I have added, right? I control everything about the titrant. The analyte is the thing that you are investigating. The analyte, you can choose a specific volume. I'm going to take a sample from the creek. I'm going to take a 100 milliliter sample from the creek. I choose the volume that I take from the creek, but I don't choose the concentration? That's what I don't know. That's what this whole lab is designed to figure out, right? So I do know the volume because I've measured it out, but I don't know the concentration, and that is the goal of this investigation, to figure out what the concentration of my analyte is. You'll also hear this term equivalence point. So an equivalence point in a titration is going to be signaled by the color change, or you hope it's going to be signaled by the indicator change. We do have to choose our indicator carefully because not all indicators change color at the same pH. Sometimes this reaction happens earlier, sometimes this reaction happens later. Remember, indicators are weak acids, right? So weak acids all come with their own Ka. They all come with their own ratio of products to reactants at equilibrium, and that ratio there, the equilibrium for each indicator will be different. And so we'll talk a little later on about how do you choose an indicator. Now the pH where the indicator changes color is actually called the end point. Okay, the place in your titration where amount of acid equals base. So when the concentration of acid equals, the concentration of your unknown acid equals the concentration of the base you have added, that is called the equivalence point. And your goal in designing your titration is that your endpoint and your equivalence point are going to be at the same place, at the same pH. So those two terms are very close to each other. You must know the difference. Endpoint is where the indicator changes color. It's solely dependent on the Ka of the indicator. The equivalence point is where the weak acid concentration is equal to the base concentration. Your analyte concentration is equal to your titrant concentration. And that is where both the analyte and the titrant are perfectly neutralized. At the equivalence point, you have only water and salt left. And hopefully you have chosen an indicator whose endpoint is the same as your equivalence point. And like I said, we'll talk about how to make sure that happens a little bit later. Okay. Of course, you know the vocabulary term indicator. A pH curve is going to be this thing we talked about when you're tracking pH through a titration, also known as a titration curve. So those are the terms you're going to hear thrown around inside this process. It's worth working those terms out so that you can functionally use them and you don't have to go look them up every time. Okay, so we're going to look at two case studies. We're going to look at titrating strong species with strong species, and then we're going to titrate weak stuff with weak stuff. Now, actually weak with strong. So before we get going, let's look at our options, right? We have lots of options of things we can mix, and you want to be able to deal with the math behind all of them. You could mix strong acid with strong base. You could also mix, weak acid with strong base, or a strong acid with weak base, or a weak acid with weak base. Okay, so these are kind of our categories, and the math is going to change slightly within these categories. Think about the math here. When we mix strong species with strong species, we have two things present that are going to force our reaction to go forward until one of them runs out, right? And then when one of them runs out, you have something else that's going to push forward until it's completely dissociated. So the math for this one is going to always go to completion, whether you have the strong acid present by itself, the strong acid, strong base present together, or the strong base present by itself. All three of the scenarios in there are going to drive to completion, not equilibrium. Whenever you mix weak species with strong species, you actually have a mix going on here. If the strong species is present, it drives to completion. If the strong thing runs out first and you're left with weak stuff, then the weak stuff goes to equilibrium. So you could see a scenario here where you go to completion and then to equilibrium. Or if your strong species drives to completion and your weak thing runs out first, then instead of going to equilibrium, your weak stuff is just going to be used up, and your strong thing that's left will go to completion. So you have a couple different options as to how that math can go, and you need to be aware of what's present. Is it strong and going to completion? Is it weak and going to equilibrium? You need to be aware of what's present and how it's going to act before you can decide how to deal with the math. Okay, and then lastly, we could have a situation where we're mixing weak stuff with weak stuff. This will always go to equilibrium. If the acid is present by itself, it'll go to equilibrium. If the acid and base are mixing, they're going to react and go to whatever's left will go to equilibrium. If the weak base is present by itself, it will go to equilibrium. So whenever you have weak stuff with weak stuff, it'll just go to equilibrium. Okay, so in this first scenario, we are going to mix strong stuff with other strong stuff. Now, as you look at titration, the thing we care about in titration is pH, right? pH may be the concentration of what's there. Like in a titration, our end goal is to figure out the concentration of our analyte, right? So the thing you really care about is pH, also known as your H+ concentration. So that's the thing we're tracking. That's the thing we're trying to calculate in our math. That's the thing we're graphing. pH is going to be graphed here. So when you start mixing this stuff, the first thing you look at is the pH of your analyte. Now that's going to determine where you start on the graph. Is your analyte an acid? Then your pH will be low. Is your analyte a base? Then your pH is going to be high. So just by looking at your graph, you can automatically tell me what your analyte is going to be. Okay, so after let's say our analyte is going to be an acid, then we're going to add a little bit of base. The base will react to completion. It will run out first. We'll be left with acid, but we'll be left with a little bit of acid, right? So our pH will have gone up because we have less of our acid present. Some of it's neutralized, some of it's still there. And then when we hit this point where we've added enough base to neutralize our acid, we're going to be at our equivalence point. And we will have only salt and water. The pH that's there is going to be determined by the ions that are present, right? The strong base, let's say it's NaOH, one of the ions that will still be present and floating around is going to be Na+. If our strong acid is HCl, one of our ions that will be present and floating around is Cl-. Now, when you're dealing with strong acids and strong bases, do these ions affect the pH? No, conjugates of strong things are useless things. So the pH in this scenario is going to be determined by water. Water is going to be the strongest species present because our conjugates are not stronger than water. Now, this is not always the case for every titration, but it is always the case for titrations with strong acids and strong bases. Then as soon as you add more strong base, you have neutralized all your strong acid. The minute you add strong base, your pH is going to spike because all you have left now is base, right? It's just base dissociating completely in water. So this is what your strong acid, strong base titration will look like. Now, after we go through a case study for strong acids and strong bases, we're going to do this same thing with weak acids and weak bases. So know that that's coming, but we're not going to deal with it yet because I want to look at the math behind the strong acid, strong base situation. Okay, so we're going to look at a case study. You're going to make a graph, or we will make a graph together. The x-axis is always your independent variable. That's the thing we're changing. We are adding NaOH. So our x-axis is going to be volume of NaOH added. Our pH is our y-axis is going to be our independent variable. It's changing as a result of our actions, right? So that's going to be pH. The pH is changing because we're adding sodium hydroxide. And then here's some information for you. Our analyte is here, our titrant is here. Now notice in this case, we know the volume of our analyte, which we always know, but this is surprising that we are given the molarity of our analyte. This is not something we usually have in a titration. Now, we're going to give it to you in this titration because we want to use this as just a case study where we watch the progress and watch the math behind it, right? We're going to calculate pH in all of these things. So for the sake of an example, we're going to give you the molarity of the strong acid, which you don't normally have in a titration. Okay, and then notice you have your molarity of your titrant, and then the volume of the titrant will give you at each step. Step 1, here's how much base we've added. Step 2, here's how much base we've added. Okay, so here we go. Here are all the points we're going to talk about. So here's point A, point B, point C, point D, point E, point F, point G. Notice at all of these points, we always have the same volume and molarity of nitric acid. We always have the same molarity of sodium hydroxide. Those things are consistent. The thing that's changing is our volume of sodium hydroxide. It is changing every single time. Now, I don't want you to sit there and watch me do this. I want you to try it and then come back and look at my math, and then try it, come back and look at my math. But get to a point where you have the pH of that point before you come and watch my math. Okay, one other word to the wise before we actually get started on this. Remember, when we're dealing with ice charts, we take our final thing and we plug into Ka, right? Well, when you're dealing with Ka, you must be dealing in concentration. Notice in this case, because we are adding a certain volume, a different volume of sodium hydroxide every single time, notice our volume is going to change, our total volume of the solution, and molarity is going to be moles per volume. Well, if this volume is changing, then that means your molarity is changing. So we are going to have to recalculate molarity for our initial concentrations at every single point, because as we add volume, our molarity is going to change. This is not something we've had to do before. Welcome to titrations. You got to understand your context before you can plug and chug into the math, right? Okay, so try a point, come back and look at my math. Then try your next point, come back and look at my math. But I want, by the end of this, my hope is that you can beat me to the math every single time. Here we go. Okay, point A, no sodium hydroxide is added. So when I look at my reaction, I only have nitric acid and water. So my reaction is just going to be nitric acid reacting with water. There's no base for it to react with, so I'm not including base in my reaction. Okay, so I have 50 milliliters of 0.2 molar nitric acid. Now, I know my molarity. I'm not adding anything to it, and so I can just keep that molarity in the beginning. My change, since it's a strong acid, it's going to drive to completion. So my change is going to be the complete 0.2. My final, which in this case is also my equilibrium, is going to look like this. I have my H+ concentration. I can plug that into my pH equation, and I get an answer. Okay, here we go. So I have a pH of 1 here on my graph. That's going to be a pretty low pH, probably my first notch. Okay, now I get to point B. I'm going to add some NaOH in here. So my reaction has to change, right? I no longer have just acid present, so I need a totally different reaction. I have nitric acid present, I have sodium hydroxide present. They're going to react together. Now, you can do what I've been telling you to do all along and think, okay, this is going to separate into H+ and NO3, and I'm going to have those two things present. This is NaOH-. Those two things present, what's going to affect the pH? H+, OH-, and you can write your reaction like that. H+, OH- forms water, right? Or you can write it as if you are including both. HCl, NaOH goes to H2O plus NaCl. It doesn't really matter how you write this. What matters is what's left over in the end and what's determining pH. So before we can figure out what's left over in the end, we have to figure out what actually reacts. Now, I have HCl and NaOH. I have 50 milliliters of 0.2 molar NaOH. I have 10 milliliters of 1 molar NaOH. Now, I have options here. I can deal with this whole chart in moles and switch it into molarity at the end, or I can just deal with molarity in the beginning. So let me show you both ways since this is the first one. Okay, so for HCl, how many moles do I have? I have 0.2 moles per liter times 0.05 liters. That gets me into moles of HCl. So 0.2 times 0.05 equals 0.01 moles of HCl. Now, if I want to turn it into molarity right away, which personally I do because I'll tend to forget to do it at the end before I plug it into Ka, I just get into a habit of turning it into molarity right away. I need to put it over its new volume. The new volume of solution is going to be the total volume of solution. So my total volume is going to be the volume of the acid and the volume of the base together. So 0.06. So if I divide that answer by 0.06, then I get a new molarity of 0.167 molar. And this is my initial amount of HCl. So notice what I did here. I multiplied the volume and the molarity of my acid to get my moles of acid in solution, and then I divided by the total volume of the solution to get my new molarity of the acid in the solution. It's kind of a lot of work, I know. But since your volume is changing, your molarity is also going to change, and you have to take that into account. We're going to have to do the same thing for NaOH. So we take our initial molarity of NaOH times our initial volume of NaOH. So that's 0.001 moles. So remember, I have moles per liters times liters. The liters are going to reduce out, and I'm left with moles. I'm going to divide that by the total volume of the solution to get my new molarity of NaOH in the solution. So that's 0.0167 molar NaOH. Okay. Whew! I have my initial quantities. Now I look at my change. What's my change going to be? My change is going to be all of one of them, right? It's going to drive to completion until something is gone. So what's going to run out first? My bases. So minus 0.0167, minus 0.0167. They're a 1-to-1. I ignore water, plus 0.0167, and let's see, 0.167 minus 0.0167 is 0.1503. I have none of my base left. I have 0.0167 of my salt. Now my salt is not going to affect the pH, but my strong base will, strong acid. So that is my pH. That's my hydrogen concentration. I take the negative log of that, and I get a pH. This was a pH of 1, and this is a pH of 0.823, which doesn't make sense. I added base, my pH should go up. Let me double check point A. My pH of point A is going to be negative log of 0.2. Oh, which is not 1, which is 0.699. There we go. Okay, that looks better. Sorry about that. So my pH of point A is 0.699. My pH of point B is 0.823. Okay, so now you see the process. It's really just a simple ice chart, right? Tracking who runs out first, acid or base. The trick here is that your initial volume, when you combine these two things, your total volume of solution is going to change, which means your molarity of each thing in the solution is also going to change. And you have to account for that before you do the ice chart. Okay, now moving on, it's going to look very similar. HCl will actually have the same starting concentration every time. Oh, nope, it won't, because our volume is going to change. So we can tweak this slightly. Okay, so instead of having a total concentration of 0.06, we're going to have a concentration of 0.07, and same thing on our base side. And since our salt is not affecting our pH, I'm just going to kind of ignore this side until we need it. 0.07. Okay, so let's do the math here. So acid is going to be 0.01 divided by 0.07. Oh. Which is going to be 0.143. Base is going to be 0.1 times 0.02 because we've added more. So 0.002 divided by 0.07 equals 0.0286. Okay, so that's going to be my change now. I'll have none of my base left. 0.143 minus 0.0286 equals 0.1144. Let's take the log of that, and I get pH equal to 0.942 at point C. All right, let's keep going. Same thing, but with 50 molar NaOH added. Okay, so 0.50 plus 50 gives me a 100 milliliters now. So this is going to be 0.05 divided by 0.1. So minus 0.05 minus 0.05 gives me 0.05 down here. Oh. And that gives me a pH of 1.3. And moving on. All right, now we're adding 100 milliliters. This is point E. 100 milliliters of base added. Okay, so 100 plus 50 is 150, 0.15. So I've added 0.1. It's going to be a 0.01 divided by 0.15. Is 0.067. Oh, and it's the same, 0.067. So my change is 0.067, 0.067. I'm left with none of each. So if I have no strong acid, I have no strong base, what is present to affect my pH? Water. Water is present to affect my pH. So in this case, we are dealing with the autoionization of water, which I know the Ka for that at 25 degrees Celsius. I know the hydrogen concentration of that at 25 degrees Celsius. I can plug that in for my pH, and my pH is going to come out to be a pH of 7. Okay, huge jump between point D and point E from a pH of 1.3 to a pH of 7. Let's see what happens next. All right, I'm going to erase this water to clean it up a little bit. All right, let's look at point F, 150 milliliters added. If 150 milliliters have been added, that means my total is at 200, so 0.2. So 0.15 added, 0.2 total. I get 0.05 molar acid. This is 0.015 moles of base divided by my total volume now, which is 0.075. And my change is going to be the one that runs out first, which in this case is going to be acid. I get no acid left. 0.05 change. I'm going to have 0.25 or 0.025 of my base left. Now, if I take the log of that, I get a POH. And then if I subtract it from 14, I get a pH. My pH at point F is 12.4. Again, another huge jump, 7 to 12.4. Okay, let's do one last point, point G. Let me erase. Okay, now I've added 200 milliliters of base. And let's see how that changes calculations. Okay, so my total volume is now 200 plus 50, so 0.25, 0.25. I've added 200.2 liters of my base. So I get a 0.02 here. So this is going to be a 0.04. Okay, this is going to be a 0.08. My acid will run out first. I'll get 0 acid, and then 0.04 is left for my base. I can take the negative log of that and get POH. Then I take 14 and subtract it, and I get a pH of 12.9. So interesting. I made the same jump between E and F, right? 100 to 150 was 50 milliliters of base, and my pH jumped from a 7 to a 12.4. So 5.4, a 5.4 jump in pH. Between point F and point G, I also added 50 milliliters of base, but my pH only changed between about 0.5. Super interesting. That would be an interesting thing to think about. Why does that happen? Why can we have the same increase in base, but the pH doesn't change the same? Okay, so lots to think of off of this page. Hopefully you're comfortable with that math. You're comfortable recalculating new molarities. You're comfortable figuring out which one's going to run out first. You understand that the change is always going to go to the death of one, right? It's going to push to completion because we're either dealing with a strong acid, strong base neutralizing each other, where one of them's left over, we're left with a strong thing in the end. Or, those are our two cases. There's no or, it's just that. And so your change is always going to be the one that runs out first. And then the one that's left is going to dissociate completely. And the ion that determines pH comes from that thing. So we can just plug the concentration directly into pH. All right, let me know what questions you have off of those concepts. Let me know what questions you have off of that math. The next one we're going to do is the weak with a base, which will add a little bit of complication. So getting this one down and really understanding what you're doing in this one is helpful before we move on to the next one. Let me know what questions you have.